Begin now. Good afternoon, everyone. Welcome to another session of the Network Seminar Series hosted by the Center for Networked Intelligence at the Robert Bosch Center for Cyber-Physical Systems, IISc. Today's talk is by Professor Ketan Rajawat, and he will be speaking on Sharpened Quasi-Newton methods with explicit superlinear rates. Professor Ketan Rajawat received his BTech and MTech degrees in electrical engineering from the Indian Institute of Technology, Kanpur in 2007, and his PhD degree in electrical and computer engineering from the University of Minnesota in 2012. He is currently an associate professor in the Department of Electrical Engineering, IIT Kanpur. His research interests are in the broad areas of signal processing, robotics, and communication networks, with particular emphasis on distributed optimization and online learning. His current research focuses on the development and analysis of distributed and asynchronous optimization algorithms, online convex optimization algorithms, stochastic optimization algorithms, and the application of these algorithms to problems in machine learning, communications, signal processing, and smart grid systems. He is currently serving as an associate editor with the IEEE Transactions on Signal Processing. He is also the recipient of the 2018 INSA Medal for Young Scientist and the 2019 INAE Young Engineer Award. Before we move on to the talk, we would like to request the audience to subscribe to our Google group for information on future talks. You can also visit our website for more details. I'll be pasting the links in the chat box. Please do check. Finally, we request the audience to keep your microphones on silent for the duration of the talk, except when asking questions. And for questions, you may unmute yourself and ask Professor Rajawat directly. Over to you, Professor Rajawat.
Okay, thank you. Thanks a lot for the nice introduction, and thanks for inviting me for this talk. So this is about quasi-Newton methods. So not only will I discuss the work that we have, but also like some background about Newton methods. So more of a pure optimization flavor. So this work is done with my colleagues. I started the work with Alec, and then at a later point, Aryan and Kivling joined. So let us begin. If you have any questions, you can just directly ask anytime. So we are considering a simple unconstrained optimization problem. X is in vector in d dimensions, and we are trying to minimize f of x. And I'll just upfront state the assumptions. F is mu strongly convex and L smooth. So you can write it as Hessian between mu I and Li, so that the condition number is given by L by mu. And then we also have this assumption on M Lipschitz continuous Hessian. In our work and later works, it is more common to assume this strongly self-concordant assumption, which is which you can also make. So Lipschitz continuity implies this strongly self-concordant. But anyways, I mean, I'm just stating Lipschitz continuity because that's easier to explain to everyone. So we already know that there is a huge class of algorithms, gradient-based algorithms, which first-order algorithms whose convergence rate, which means after t time instance, the optimality gap grows or decays as some factor which is less than 1 minus 1 by root kappa, for example. So something that is less than 1 raised to the power t. Right. So this is called linear convergence. And we already know that gradient descent or accelerated gradient descent in particular has this convergence. And also the first order methods have have complexity, which is linear in D. D, recall, is the dimension of X. So, you need to process each element of X and gradient of f of X. So it's approximately linear in D. Okay, so this is all about first order methods. Then we also have the second order method, which is the Newton method. Now in Newton method, you have update is given by Hessian inverse times gradient. It is known that Newton method is very fast. It has a local quadratic rate. The rate is local in the sense that wherever you start, the rate will not immediately be quadratic. There will be a phase in which the function value will keep on decaying, but not at a quadratic rate. And then suddenly it will become quadratic. After some point, it will become quadratic. So that is why it's called local. All the Newton method and all the other variants have this phenomena. They have a local quadratic rate, which means that there is a phase which is where slower convergence, and then suddenly it becomes fast. And the computational complexity of Newton method is order dq. It is dq because generally you need to do two steps. One is you need to calculate the Hessian. Calculating the Hessian may be order d square, because each element you need to calculate. But then you need to solve this system of equations in order to find this direction. And solving this system of equations will require order dq. Right, so this is the Newton method. We all know this. And the problem that this is order dq, to solve this problem, there have been a lot of proposals of quasi-Newton method. Right, so quasi-Newton methods have been popular since very, very long ago, 50s. The idea there is that instead of using the Hessian, you use some approximation of the Hessian, let's say GT inverse. Instead of Hessian, you use GT. So that GT inverse is easily calculated. So you can easily calculate this whole direction. And it should, I mean, because the quasi-Newton method, ideally it should get quadratic or at least superlinear rate, better than linear rate that you can get using gradient descent. And the computational complexity should be smaller. It cannot be dq because that's too large, prohibitive. So it should be d square. I mean, we can expect it, we cannot expect it to be less than d square because there is a Hessian involved with d square entries. So you need to at least, process each of the entries. Unless there is a very special structure like low rank or something, you need at least d square computations. So we can expect that it can be at least, so we want that it should be at most d square. We don't want it to be higher than d square. Right? So this is all about quasi-Newton methods. So this is the requirement. So I'll then now talk about various quasi-Newton methods that have been proposed in the literature. In fact, I'll only talk about the first one, let's say. So William C. Davidson was a physicist and mathematician at Argonne National Labs. So he was the one who came up with the first version of the quasi-Newton method in 1959. So the original paper was submitted, but it was rejected because it used some notation which was not common at that time. And also it used some kind of hunting metaphor to explain the whole work. And then that hunting metaphor, I mean, to me, it made things more confusing than illustrative. So there were a lot of comments. And then finally, it was published in 1991. And in the 1991 version, there is a preface included which described that the original version was not up to the mark and what were the comments received in the original version. So anyway, the reason it was published later in 1991 was because in 1959, it was followed up by Fletcher and Powell, who did a lot of work on the quasi-Newton method, proved the convergence. In the 1959 version, convergence was not proved. And they showed that it is actually better than other gradient methods, for example. So this became to be known as the DFP method, Davidson, Fletcher, Powell method. And then since then, there have been other versions of quasi-Newton methods. There is a very interesting story about William Davidson. He was actually one of the group of citizens, it was called a citizen group, who broke into FBI in 1971. So 1971 was before Watergate. It was the Hoover era. So it's a very interesting story, and it exposed a lot of documents. All the documents that they stole, they leaked it, and the burglary was planned in such a careful manner that no one was charged ever, despite lot of investigation. There's a very unexpected link between this, and you cannot expect, like no one expected that you would get such a link between a physicist, a normal physicist, and an FBI break-in. The 1971 is the name of the movie you can watch to learn more about this. Okay, so moving on. we have the, let's say, a quasi-Newton template. So this is the template followed by all quasi-Newton methods. They start at some x0 and some initial guess of the Hessian. Usually it is some scaled version of identity. Then this thing is solved, GST equal to gradient fxt. It is assumed that GT is such that this is easy to solve. There are ways of doing that. We'll discuss that. Then there's the update, which is the usual xt plus 1 equal to xt plus eta times st. Or you could say minus if you remove the minus from here. And then finally, there is an update of GT itself. So GT is updated to GT plus 1. And this update, the way in which this update is carried out, varies across quasi-Newton variants. Okay. So there are ways of updating what we can do. For example, if you remember the Sherman-Morrison formula, you can make a rank 1 update and calculate the inverse of a matrix in time that is, or in complexity that is order d square rather than d cube. So if you have A inverse, you can calculate the inverse of A plus VV transpose. Right. So this is called the rank 1 update formula, or Sherman-Morrison formula. And in the same way, you can do rank 2 update also. So most of the quasi-Newton methods do rank 2 updates, which means that they apply this 2 times. Right. So still complexity is order d square, or you can think of it as Woodbury update. So this is the main idea of most of the quasi-Newton methods. The Hessian approximation GT. So you maintain the inverse of that. And each time you update GT, you do a rank 2 update. Right. So for example, so let's look at this idea of approximating a matrix. So what does it mean to approximate a matrix? So suppose that we have some G which approximates a matrix A. A can be your Hessian, let's say. Right. So what we want to do is go from G approximately equal to A. We want to update, looking at A at some point, Hessian at some point, we want to update from G to G plus. And now G plus should better approximate A. You can think of it like this. So G plus is G plus some low rank terms, right? This is the form of update that we want because we want to apply Sherman-Morrison or Woodbury identity. Right? So if we use this form of update, then if we are maintaining G inverse, then we would be able to update it to G plus inverse, and that will allow us to carry out the update. So the BFGS style update, the BFGS is a special class of quasi-Newton methods, Broyden, Fletcher, Goldfarb, Shano. So BFGS style update is of this form. Oh, I forgot this point. Yes, so beyond more than just updating G from G plus, we also want to impose this quantity. So why do we want to impose it? See, there are infinite number of ways in which I can approximate G plus, or I can update G to G plus using a low rank update. So there are infinite number of ways of doing that. So you could say that we want to restrict our ways of updating into a smaller class. Now there used to be a method, popular method called secant method. So from the secant method, this idea was imported or inspired from, which said that let's pick a direction and we will impose that along this direction, both A and G plus match. So U here is the direction, and along this U, both A and G plus will match. So BFGS update, for example, which is given here, ensures this. It ensures that along this U, G plus and A match. Right? So each time the Hessian is updated, each time I will ensure that it matches the Hessian along a certain direction. So that is the whole class of BFGS updates. This is very interesting because even though there are infinite number of ways of updating G plus from G, this particular way of updating allows us with certain flexibility in the proof. Also, it allows us to develop this algorithm. In this particular result allows us to develop the proof. Okay, and you can verify that this kind of update will actually satisfy this inequality. You multiply both sides by u, you will get g plus u equal to au. Okay, so let's look at the BFGS, classic BFGS update. So classic BFGS is the BFGS algorithm. In that, generally what we do is we set u equal to xt plus 1 minus xt, which is the descent direction. So this is the descent direction. And we set a, instead of the Hessian, we use the average Hessian. Average Hessian is what? It's basically the integral of Hessian from xt to xt plus 1. Right? Or average, you could think of it average of the Hessian between these 2 points. Then this condition, g plus u equal to au, this condition is written like this, called the secant condition. Gt plus 1 into xt plus 1 minus xt equal to the difference between the gradients. Right? So if we use this, then the BFGS update looks like this. Now there's something very interesting about the BFGS update, which is that we actually don't need to calculate JT. The average Hessian, we actually never need to calculate. In fact, the update also does not need the Hessian at all. It's basically entirely dependent only on the gradient at xt and gradient at xt plus 1. Xt plus 1, remember, you've already updated. So you only need to calculate the gradient at xt plus 1. Xt gradient you already have from the previous iteration. So this is the BFGS update. Right? Essentially what it is doing is it is constructing an approximation, which is GT, along the descent direction. And each time, each iteration, the approximation is improved along the direction in which the method is descending. Because this is the classic BFGS update. If you look at it carefully, you can see that there is indeed order d square complexity, because these are all matrices. You just need to calculate these matrices and add to GT. And GT inverse, we already saw that from the rank 2 update of the Sherman-Morrison, it has order d square complexity. The whole thing, each iteration has order d square complexity. So Hessian is not required, that's another thing. And the classic BFGS, actually the asymptotic convergence was known, but the exact rate of convergence was not known until recently. So it was established in this paper that the exact rate of convergence, now here the metric is also very, you could say strange, but it's something related to gradient. It's a particular kind of norm of the gradient. So it's d log kappa divided by t. Kappa is the condition number. So this is d log kappa divided by t raised to the power t. Right? D log kappa divided by t is something that is less than 1. So this thing is raised to the power t. And this is in fact superlinear convergence. It is faster than linear. In fact, you could express it as e raised to the power some constant times t log t minus e raised to a minus constant times t log t. So e compared to e raised to a minus constant t, it is slightly faster. There's a log t term there in the exponent. Right, so that is the classic BFGS rate. Now it is interesting that the result, the exact rate, it's also local, but the exact rate was established only recently. And the main idea in establishing the rate was the choice of a particular metric which is used for establishing the rate. Here you can observe that this rate will be superlinear, provided that this quantity is less than 1. If this quantity is greater than 1, at that point, this bound is not very useful. So you could say that when t becomes d log kappa, this bound becomes useful. So that's where the rate becomes actually superlinear. So this is the delay. You could say this is the delay starting from time t equal to 1, iteration t equal to 1, till d log kappa, you need to wait. Till from there to there, the analysis has to change. Our analysis is basically changed, and you can show that it is linear in that case. And after that point, it becomes superlinear. This is quite a good result because it depends logarithmically on the condition number. It depends on the dimension, but only logarithmically on the condition. And one thing that has become clear from this analysis is that the Hessian is being approximated along the descent direction only. I know we said that we started with this assumption. We started with saying that we'd only approximate Hessian along the U, and U was the descent direction. But it actually turns out in the proof that this is also what is happening. So inadvertently, it does not happen that Hessian gets better along all directions. It actually is getting better only along the descent direction. So let me quickly discuss the proof, right? I'll not give all the details of the proof, just a very rough sketch of the proof, because this is a new result and I want to just tell you how exactly it works out. So there are two key definitions. One is the merit function, which I was mentioning here, the norm of gradient, but the matrix that is used for weighing that norm is the Hessian inverse. So it's a very strange metric. And this is what is being used. And interestingly, it is because we are using this metric that we are able to establish those kind of results. Previously, people didn't use this metric and we only had asymptotic results. So it's perhaps it is because of this metric that the proof works out. And then there is also a trace potential function that we will use. It's very useful. It is basically the trace of Hessian inverse into GT. It's measuring how far GT is from Hessian inverse, because if you can see that if GT is equal to the Hessian inverse, this is 0. And in fact, if GT is more positive definite than Hessian, then this is 0 only under that condition, only under the condition that these two are equal. Okay, so this you can say as the quantity that measures how far GT is from Hessian. So just to recap, we are at Quasi-Newton method BFGS, classic BFGS, and we have introduced two metrics. And the proof of convergence or proof of the rate, explicit superlinear rate for this one follows like this. In the first step, we are basically verifying that the merit function. So I'm only providing the proof for quadratic case. I'll tell you what is the difference in the general case. The quadratic case is a little bit easier to explain. There are a lot of small things that I need to add otherwise. So in the quadratic case, when objective function is quadratic, it turns out that the merit function is related to the previous merit function like this. So it's multiplied by theta t, and theta t you could say is measuring the difference how far GT is from JT along this direction xt plus minus xt. Okay, and it's a bounded quantity. So because it is bounded quantity, something bounded by less than 1, linear convergence is obvious from here, right? Then actually one step that the key inequality that they show is that sigma t plus 1 is less than equal to sigma t minus theta t square. Remember, sigma t plus 1 was the trace function, which was measuring how far GT is from the Hessian, or in this case JT. And we are saying that it is decreasing by theta t square, right? Now, this is very interesting. If you look at these two inequalities, you will find that it's very interesting. If theta t is large, then this decreases by a lot, right? But if theta t is small, then obviously this lambda is decreasing quickly, right? So we can't lose. Once we have these two inequalities, we can't lose. So basically, the rest of the proof is very simple. You just take a telescopic sum. Summation of theta I square is less than equal to sigma 0 minus sigma t plus 1, which is less than equal to sigma 0, which is less than equal to d kappa. So this is one inequality you can show. And then once you have theta t square, you just put it here. You just apply this inequality recursively, right? Theta t square summation is bounded. So if you apply this inequality recursively, apply AMGM inequality, you get something like average of theta square. And then, you just have to substitute this and you get the required rate result, which is d kappa divided by t raised to the power t by 2. Okay, so this is the overall idea of the proof. This step also, although this is the key step, I've not shown the proof. It's not very complicated to prove. And in the general case, it's not very different. It's just that these inequalities become a little bit harder. This becomes an equality. Equality becomes inequality. And other inequality is a little bit harder, but not very much. In this paper, they use actually a different potential trace function, not sigma, a different function, but the observations remain still the same. And they actually use a different, even more different function. So if you remember, I was mentioning actually a rate of d log kappa, but here this one shows d kappa. If you use a different potential trace function, then you can actually show d log kappa. So that they proved in another paper. Okay, so the important thing to note here is that everything depends on what trace function you are using. So it's not that different functions are decaying at different rates. It's probably more likely that your proof for one trace function is working better than the others. Right? So the proof for this potential trace function that they use in the third paper is probably better or more tighter, and that's why it's giving you better results. The algorithm remains the same, only the trace function changes. Okay, so this is all about classic BFGS. I'll mention some observations, but let me pause for a second to see if there are any proofs, any questions.
Excuse me, what is kappa?
Kappa is the L by mu condition number. Here.
Ah, okay.
So typically everything depends on L by mu. It's very ill conditioned. You can expect that it will be slower. But yeah, we want logarithm dependence on kappa, not linear dependence. Okay, there are no more questions. Let me just go to beyond classical quasi-Newton, classical BFGS methods. So classical BFGS, as we have already seen, it's known since a long time, and but only now we are able to say that it is achieving this particular superlinear rate. Now, as I was mentioning, the rate, you can say that it is e raised to the power some constant minus times some constant times t log t, which is just a little bit faster than e raised to a minus constant times t, right? It's a little bit faster. T log t is there. It's not very much faster. In contrast, Newton method has quadratic rate. It's e raised to power minus e raised to power t. It's much faster. So there's a huge gap between classical quasi-Newton rate and actually Newton method. It's a huge gap between those two rates. And this was something that was not known earlier. We only said that, empirically it was known, obviously, but we only said that, it's theoretically we just talking about superlinear asymptotic rate, but never about the actual rate it is achieving. So there are a few observations that we can make from the proof that will tell us that why it is like this. So the key inequality, as you remember, we were using was that sigma t plus 1 is less than equal to sigma t minus theta t square. Right? So this inequality said, so if you look at this inequality, you can say that suppose sigma starts at some point, and I keep on proceeding with the iterations. The theta t square is the negative term that will accumulate. Sigma t is obviously greater than 0. So theta t square definitely is going to 0. Recall that theta t square was what? It was the error between GT and JT. GT was the approximation of JT. JT was the average Hessian. But along this direction, xt plus 1 minus xt. So it was the error along this direction. Now, from this inequality itself, we can see that theta t square may go to 0. So the error may go to 0 along the descent direction, but that does not imply that sigma t will go to 0. Remember, what was sigma t? It was trace of Hessian inverse GT. It was a difference between GT and Hessian. Right? So trace of Hessian inverse GT minus D. So the GT and the Hessian, that error, overall error, does not go to 0, but it goes to 0 along this direction. Right? So because classic BFGS is able to reduce this error along this direction, it is able to converge superlinearly. But there are gaps here. Particular gap is that sigma does not decrease to 0. Now, what can we do to avoid this situation? In fact, we want sigma to go to 0 also. By saying that sigma goes to 0, we could say that our Hessian approximation is increasing with iterations. And if Hessian approximation increases with it becomes better with iterations, then definitely we are getting closer and closer to Newton method, the actual Newton method. So it turns out that there is an inequality that was established in one of the works, which is that if you start at some G and then you go to G plus, the error is at least, the reduction is negative of the reduction is at least this much. Now, if you want to minimize this, it makes sense that you should not choose xt plus 1 as minus xt as u. You should not choose this as u. In fact, you should choose a u which should minimize this quantity. The right-hand side that we are getting, we should ideally minimize that quantity. Now, obviously, minimizing that quantity with respect to u is hard, but what the Greedy paper suggested was that instead of choosing arbitrary u which minimizes this, you choose u from one of the standard bases, like ei is all zeros, but 1 at the ith location. So you choose u from among the standard bases and choose one of these. So then this step is very easy. Actually, all you need to do is you take the diagonal elements of G, take the diagonal elements of A, divide those, and pick the one that is the largest. Pick the one where the ratio of the diagonal elements of G divided by diagonal elements of A is the largest. And that's your direction. That's your greedy direction. And you substitute this EI, you substitute into the BFGS equation. Remember the BFGS equation, which was the rank 2 update. If you substitute it here, it is possible to establish that the sigma, which was the difference between A and G, you could say A inverse G, trace of A inverse G, that quantity decreases linearly. Right? So this was the whole idea of the greedy BFGS. And in the greedy BFGS, they were able to establish that the same metric that we were using earlier, Hessian weighted gradient norm, the same metric is going down as something, some constant. So if you ignore this one, you have some constant raised to the power t square. Right? So this is much, much better than t log t. Earlier we were getting. It is more like e raised to a minus constant times t square. It also has order d square complexity. Why does it have order d square complexity? Because if you look here, we will not use A as Hessian average, we'll actually use it as Hessian itself. So this would require one diagonal of the Hessian and one diagonal of G. So this will have order d complexity only. But this step would still have order d square complexity because you need to construct that whole matrix. So overall complexity is order d square. And it is reaching that order e raised to a minus constant times t square convergence. The con here is that this whole thing should be less than 1 in order for this to work out. And that requires d kappa log kappa iterations to start the superlinear convergence phase. Which means that superlinear convergence for greedy BFGS starts much, much later. Remember, it was starting at d log kappa. In the classic BFGS, it starts d kappa log kappa in the greedy BFGS. So if a problem is such that kappa, which is the condition number, is large, then your superlinear convergence phase for greedy starts much later. So you'll be linearly converging for a long time, then you will become superlinear. Okay, so this is the main disadvantage of greedy BFGS. Okay, I'll quickly present the proof sketch. Here, what is happening is we are proving this thing. We are proving that GT stays very close to Hessian and 1 plus sigma t times Hessian. And remember, sigma t is going down linearly. And then we verify the same kind of inequality as earlier, but theta t is replaced with sigma t. For the greedy step, we already saw that this holds. So if you apply it recursively, you can show that 1 minus, this is a linearly decreasing term, right? Exponentially decreasing term. And then it's just a matter of applying this recursively. You have a factor, contraction factor, which is linearly decreasing. So the overall thing is decreasing as 1 minus d kappa raised to the power t square, approximately. Okay, so this is the overall idea of, this is the quadratic case. In the general case, I've not discussed the general case. There is one small thing that in order to ensure this at all times, you need to scale the GT at every iteration by a constant factor, by a factor which is depending on the Hessian. So that step I've not shown. That it sort of takes care, it makes the proof a little bit complicated, but the overall idea remains. Okay, so just to compare and recap what we have seen so far, classic BFGS rate is 1 by t raised to the power t, which is like e raised to power minus constant times t log t, and the convergence starts at d log kappa. Greedy BFGS, the rate is e raised to power minus constant times t square eventually, but the superlinear convergence phase starts much later at d kappa log. Log d kappa actually, not d log kappa. Log d kappa. Okay, so these results are shown in these two papers. So let's look at it more empirically. Like, how large is this factor d kappa? How much is the disadvantage of this quantity? So it turns out there's a lot of disadvantage. This is actually much worse. So much so that it makes greedy BFGS almost impractical for most problems. This is so bad. This T0 is so bad that it makes the greedy BFGS unusable for most problems. Right, so I'll show you one example. This is one particular data set we took and just ran Quasi-Newton method. The top one is the gradient descent, which is the linear convergence. This is the classic BFGS method, for which the superlinear convergence starts quite early. It looks linear here, but it is t log t, so it's slightly superlinear, it turns out. And then for greedy BFGS, the superlinear convergence phase starts around this 300 iteration mark. Note that by the time greedy BFGS is actually able to overtake classic BFGS, we are already at 10 power minus 10 accuracy. So, 10 power minus 10 is very low, and you may say that I don't even need that much accuracy. This Quasi-Newton could be part of an interior point method. So each iteration, do I really need that much accuracy? And maybe if I do need it, it's fine. I can achieve with classic BFGS without much problems, right? So this is the disadvantage of having this superlinear phase start so late, right? And this thing is, to further elaborate the same point, the Newton direction error, or the error along the descent direction. For classic BFGS, it continues to decrease, but for greedy BFGS, it goes down. And you can see that Hessian approximation error for classic BFGS actually remains quite high, because classic BFGS does not reduce the Hessian approximation error. That's what is the whole point. But for greedy BFGS, it is from the start itself, it is decreasing linearly, and it becomes actually faster here. Right. So this is another graph, like illustrating what we observed from the theory. Right. So I am here showing many problems for which the same issue exists. The greedy BFGS is so late in starting its quadratic convergence superlinear convergence phase, that by the time classic BFGS has already achieved 10 power minus 10 or lower accuracy. So except if you, in the first problem, it seems to work fine, but in all other problems, you can see that, it overtakes very, very late, right? So looking at these curves, and these are also justified by theory, you can argue that what is even the point of using greedy BFGS if it's going to be so late. I don't really, it requires extra thing that you need to know the Hessian diagonal entries of the Hessian and one row, one column of the Hessian. So that extra information, why do I bother calculating if classic BFG is already working well? Right. So that is the question that we started with. So we started with this question that we actually need two things. We need superlinear phase to start early, and we need the convergence of the greedy. Right? These two things. So two in one. We need one algorithm which provides these two in one, 2-for-1 deal. So the main idea of our work, which is very simple, you would say that that's it, but it's that you apply classic and greedy BFGS update one after the other at every iteration. That's the main idea. And turns out that you can actually bring together both the proofs and make sure that this actually has a positive impact. So classic BFGS, the idea is that classic BFGS is supposed to improve the approximation along the descent direction. So that will improve the performance initially, and then greedy BFGS meanwhile will improve the overall Hessian approximation, and that will allow us to reach the superlinear phase at some point. Right. So the overall algorithm for the quadratic case looks something like this. This step is the same. XT update is the same, but then we do the classic BFGS update, compute the greedy direction, and then do the greedy BFGS update. So we are having two updates in the same iteration. Right. Now remember, both the updates were ordered d square. So the complexity wise, there's not much we are losing. In fact, many of the quantities that you calculate for one will also be usable for other. So complexity wise, there's hardly any difference. Of course, like greedy algorithm, we still require Hessian diagonal and one row and column of Hessian. But that's it. It's not, we don't require much. And then for the general case, the only small difference is that we need to scale our Hessian approximation by a certain amount. So this is the scaling actually it is required for the purpose. If you remember, M was the Lipschitz constant of the Hessian. So the scaling is required for the purpose of maintaining this GT greater than equal to Hessian. This was something that all our results required. So that's why we needed to scale it. And in practice, we never used the scaling, by the way. In practice, we just didn't do the scaling and everything worked out well anyway. But in theory, you do need this scaling. So again, order d square complexity in the general case as well, and Hessian diagonal and row. And the scaling, as I said, not required in practice. We can also tune the scaling if we want, but since we didn't need it in practice, we never tuned it. So this is the overall sharpened BFGS, which is called the sharpened BFGS algorithm. And if you look at the rate is pretty much a combination of these two. We get, instead of the d kappa term, we get d kappa by t term. And then this term is pretty much the same. And here we are able to not drop the kappa term, but we are able to drop it slightly by log kappa. Now, this may not be very tight. We'll discuss about this later. But it is an improvement. So just a proof sketch very quickly. The same thing as greedy BFGS. One step is borrowed from greedy BFGS. Second step is borrowed from greedy BFGS. Third step is borrowed from classic BFGS. And then you just merge the two. So instead of getting this linear only decrease, we have linear like exponential constant factor decrease minus theta t squared term. So we have both the terms, And then if you analyze it like as usual, like classic analysis, you will get the required result. Right? The general case again would have some scaling issue, so that scaling issue has to be taken care of. But that's it, not much change. And you can see from this graph that sharpened BFGS, the Newton direction error decreases similar to greedy, and the Hessian approximation error also decreases. So basically, it is able to get the best of both worlds. It's able to reduce the Hessian approximation error faster than greedy and Newton direction error faster than classic BFGS.
Excuse me, I have one question.
Yes.
What are the functions for which these graphs are drawn?
This is one logistic regression we used, logistic loss.
So it's just one function. It's not averaged over many trials or many functions.
No. We just only tested for two classes of functions. One was regularized logistic loss, and I don't remember the other one. There are two losses we considered. Yeah.
Okay.
But the theoretical results hold for any.
Yeah. Okay.
So we didn't bother with testing over many functions. Because this is the kind of performance that we then get. The sharpened BFGS remains similar to classic BFGS for a long time till the quadratic phase is not kicked in. And when the quadratic phase actually kicks in, it's actually faster than both of them combined. Right? So this is the approximate performance that we get in all the cases. Basically the best of greedy and classic. And we tested for lots of different data sets. Same function, but the data set is different. Changing the data set makes the condition number different. So the condition number is different across these. So as you can see in all the cases, basically the green curve is below the red and the blue. In fact, it starts with the red and then falls off like blue at some point. Right? So the superlinear convergence starts very similar to where it starts for greedy. This e raised to a minus 80 square convergence, but the rate initially is similar to classic BFGS. Right? So overall performance, that's why it is improved. So that is all I have. Let me just conclude. So we have the quasi-Newton versus Newton method. Well, I shouldn't say both can achieve this. So per iteration complexity of Newton method is higher, but the quasi-Newton method now has better convergence compared to existing ones like T log T, it's now T square. Of course, Newton method is much better. It is quadratic. What the non-asymptotic rate analysis, what it reveals is that classic BFGS approximates the Hessian along the descent direction only. And that's why the rate is bad. Greedy BFGS approximates the Hessian well, and that's why it achieves a better rate. Not quadratic, like e raised to a minus 80 square. Quadratic exponent is quadratic. And then the linear phase, the phase in which the greedy BFGS decays linearly, that's very long, practically long. For all the problems, it was too long to be used in practice. But this linear phase is improved by using the sharpened BFGS, which actually has a similar performance to classic BFGS initially, and then it decays the e raised to a minus 80 square rate. The key thing that we are not sure of, and we are still working on, is if the sharpened BFGS initial phase can be further reduced to d log kappa. Right? So instead from d kappa to d log kappa, because this is the one that is achieved by classical BFGS. Now the complication here is that we have to use another metric for it, and that metric does not seem to gel well with the greedy updates. So that is the complication that we have not been able to solve. So this remains an open problem. So that's all I have. Thanks a lot, and you can ask any questions.
So does this result also apply to LBFGS memory wise?
No, doesn't apply.
We still require disk square memory.
Yeah. So LBFGS is basically aimed at reducing the D square to maintaining very many rank 1 terms, so that you don't need to store the whole D square matrix. So yeah, these results do not apply to LBFGS.
Okay.
I think LBFGS, there are no existing results, non-asymptotic results at all. It's more of a heuristic. So there are no non-asymptotic results. I am not sure of asymptotic results. Has anyone proved that LBFGS has asymptotic superlinear convergence? I don't think so.
No, I don't think so. So in the graphs, I mean, I had one small doubt. So here you say that linear phase of greedy BFGS is impractically long, right?
Yeah.
But see, the blue curve is the greedy BFGS. I expected that the drop will happen after the red curve, because classical BFGS still has the linear convergence. For example, in the second graph that I'm looking at, classic BFGS is still converging in a linear manner, but greedy BFGS has started the non-linear phase. So here in the experiment, it doesn't seem to.
No. What is happening is classic BFGS has a slightly superlinear rate, e raised to minus t log t. So this is actually t log t, and it starts superlinear phase as d log kappa, which is, I guess, which is here.
Oh, okay,
It basically becomes superlinear right from the start.
Right from the start. Okay. Okay.
Which is not true for any other, right? Now, what we suspect, greedy BFGS becomes superlinear here. What we suspect is that classical BFGS, sharpened BFGS becomes superlinear here and achieves e raised to minus t log t here, right at the start, and then it achieves e raised to minus t square at some point at d kappa.
Okay. Yeah, that's what I thought.
There are three phases basically.
Right.
For sharpened BFGS.
It's just that for the classical BFGS, it's the linear phase is extremely small. Within 20 iterations, I think it's.
It's not even visible in any.
Okay.
That's what we observed also. Like if you try to, looks linear here everywhere.
Yeah.
But actually, if you try to measure it exactly, it's slightly better than linear.
Yeah. Okay.
Ketan Chandra here, just a quick question. So in the greedy BFGS, first of all, excellent talk. Thank you so much. Now in the greedy BFGS, there is a selection step, right? You're doing that maximization over all EIs. How does that figure into the analysis when you do this kind of a discrete maximization? How does that get taken care of in the analysis?
Yeah, it's a bound. It's kind of a bound that is used. I'll just quickly get to that. Yeah, it's a bound that is used for establishing this step. So basically, what happens, I don't remember the steps, but it is basically a bound that is used for this. So we replace it with, this is the maximum. So what is done is we take the difference and then we are replacing it with argmax over this is replaced with something else, argmax over something else without this restriction. Bounded by something else without this restriction. And then we go ahead with the bounding G by A terms.
Okay.
That's why L by mu comes in somewhere. Because, G by A is upper bounded by L. Yeah, I don't remember the exact steps, but that's the main idea. It's not, the discrete optimization doesn't play any role.
Okay. Thank you.
Any other question from the participants? If there are no more questions, let's end the session here. Thank you, Professor Rajawat, for an informative talk. As discussed before, we would like to remind the audience to subscribe to our Google Groups, which is the mailing list for information on future talks. You can also visit our website for more details. The links have already been pasted in the chat box. The link to the recorded video will also be posted on the webpage. Thank you and have a great day.
Thanks a lot also from my side. I really enjoyed giving this talk. I worked a lot on this proof, and I thought it's good that I have a chance to do it in front of esteemed audience such as yours. Thanks.